Guys, hope this finds you great wherever you are. I'm Ernest, and I'd like to welcome you to my channel of Ernest Sciences and Mathematics TV channel. In today's discussion, I'm going to look at a preview of course, an interesting topic of quantum mechanics. Now, this is going to be assisting us try to describe and understand the various range of topics which we are going to discuss falling under the category of quantum mechanics. Now, in a sense, this is going to be a branch of mechanics that deals with the study of motion of particles over a scale of atoms and molecules. And this is going to be backed by a range of course, experimental data which we are going to come across performed over time in trying to back up this specific aspect of quantum mechanics. And in a sense, we're going to see that this is going to be a division of the branch of physics that is referred to as modern physics. As we had said earlier in some of our videos, basically we can divide physics into two broader categories of classical physics and modern physics. Now, under modern physics, we're going to be looking at two important theories, and these are the theories of relativity advanced by Albert Einstein, and of course the concept of quantum mechanics, which is our topic of interest for today. Now, in our range of videos, I'm going to be looking at various concepts. A particular interest is going to be the atomic theory, which is going to be assisting us create a basis for the various concepts which we are going to come across under the broader topic of quantum mechanics. Now, this specific topic, we are going to be taking a keen interest on of course, the concept of the wave mechanical model, and this is one of the models that was advanced by, of course, the works of Loidy Broglie and Erwin Schrödinger. Now, in a sense, we're going to see that this relies on the fact that as from some of the experimental data which has been done, the waves are going to be behaving as particles, and particles are going to be behaving as, of course, waves. Now, Erwin Schrödinger is going to come up with an equation of trying to, of course, describe the various energies and positions and other aspect of this specific nature of particles that are behaving as waves. And of course, Loidy Broglie is going to be giving us a characteristic wavelength which can be used in order to describe the wavelength of these specific particles that are going to be behaving as waves. Now, this has been backed by some of the experiments that were done by some of the scientists, of course, in particular Clayton Davisson and Lester Gamma, who performed the experiment to support this wave mechanical model. And we're going to come across various range of other topics which are going to be interrelated to this. Now, in a sense, that described from my discussion of the various, of course, structure, of course, formation of an atom, that an atom basically is going to be consisting of a nucleus center that consists of protons and, of course, neutrons, which are positively charged and neutral, respectively. And of course, around this specific nucleus are going to be consisting of these specific particles that we refer to as electrons. Now, in a sense, we're going to be seeing the relationship between these two specific particles of electrons and, of course, protons. And we're going to see that, as we said, there are various characteristics which are going to be associated with these subatomic particles, among them which is going to be their charge. Now, the protons are going to be positively charged, whereas the electrons are going to be negatively charged. And in a sense, we're going to see that from the natural laws of attraction, we're going to expect the relationship between these two negatively charged particles concerning particularly to the forces of attraction that is going to be experienced between the two. Now, Coulomb's law provides for us a basis from classical mechanics of trying to describe the forces of attraction between these two specific particles. And in a sense, we're going to see that we can use Newton's second law of motion to try and describe the motion of this specific type of particles around, of course, the nucleus. Now, in a sense, of course, a basis that is going to be created by these two specific laws of Coulomb's law and Newton's second law of motion of describing the forces and the kind of motion around the particle can be used from classical mechanics. And later on, we're going to see that there's going to be a situation whereby these two specific laws can not give us a comprehensive way of trying to describe this specific, of course, the nature of these particular particles. Now, picture this. If we have a positively charged nucleus center and, of course, an electron revolving around this specific nucleus, then we're going to expect that there are going to be forces of attraction that are going to be particularly attractive forces which are going to be pulling the electrons from their specific positions into the nucleus center. Now, in particular, this is not going to be the case And if we try to analyze from the Coulomb's forces of attraction, we're going to see that if we try to consider the distance between these two specific particles as, of course, what we refer to as the distance is infinite, then therefore we're going to expect the forces to be zero. And if we're going to see that if we consider the, of course, distance to be, of course, zero, then therefore we're going to be having an infinitely attractive nature of a force which is going to be experienced. But if we are going to see that this is going to be the case for the distance which we have set to be the constant distance. But if the distance is going to be varying, then therefore the Coulomb's law does not provide a basis for us in trying to describe this kind of course, motion of the particles. And therefore we're going to rely on Newton's second law of motion, which basically relates to the acceleration of these specific particles under motion, described as, of course, directly proportional to the force and inversely proportional to the mass of this specific electron. Now, in a sense, if we try to do an analysis of this specific type of description given by Newton's second law of motion and Coulomb's law, we're going to see that they are going to be giving a challenge whereby the atomic theory giving this specific kind of nature of motion and force is going to be falling. And in a sense, this specific failure then therefore is going to be giving us an hint that we need another way in which we can describe particularly the motion of an electron around a nucleus. Now, this is going to be explained by the concept of quantum mechanics, which is going to be providing for us a basis of trying to describe this specific nature of forces and, of course, the kind of motion which is going to be resulting. Now, in a sense, we're going to see that basically then therefore we are going to rely on a number of theories which are going to be backing this specific nature of motion. And this, of course, is going to be culminating from what we refer to as the principles of quantum mechanics. Now, we shall look at a number of principles which are going to be assisting us trying to describe this specific nature of course, motion of these specific particles. And, of course, we shall look at ways in which we can come up with specific laws which are going to be assisting us achieve the same. Now, these are going to be the principles of quantum mechanics. And in my various discussion, I'm going to be relying on basically three aspects of the principles of quantum mechanics, which are going to be assisting us try to describe this specific nature of particles. And these are going to be the Planck's quantum theory. And this theory is going to be assisting us describe, of course, the energy form of these specific particles as per described by Max Planck, of course, whose case was particularly the study of the spectrum of black body radiation, which gave us in a sense that basically the energy of such a kind of systems are going to be quantized. Next, we shall look at the Loewy-de-Broglie hypothesis that gives basically the concept of wavelength description of these specific particles. And this is going to be assisting us in trying to treat these specific particles as waves and, of course, particles at the same time. And we're going to see that Loewy-de-Broglie basically relied heavily on the works of Max Planck energy and Einstein's energy mass relationship, which gave us the concept of this specific characteristic wavelength. Then lastly, we shall look at the concept of a wave-particle duality. And this is going to be giving us some of the experimental data, which is going to be particularly backing the aspect of this specific aspect of the, of course, double or the wave, the particle dual nature of matter. And this basically we shall look at the experiment done by, of course, Young's double slit experiment, which basically shows that if these specific particles are going to, or rather the waves are going to be considered, then they are going to be giving us the aspect of photons, which can be given in terms of light. And then we shall look at the concept of what we refer to as this specific aspect of the photoelectric effect. And this was explained by Albert Einstein. And of course, we're going to see that in an essence, if these electrons are going to be considered as waves from the, of course, photoelectric effect, these electrons, these specific photons are going to be knocking electrons off the surface of metal surfaces. And this is going to be giving us an aspect of electrons being considered as particles as well. And then lastly, we shall look at the concept of Arthur Compton's experiment on the concept of X-ray scattering. And of course, we're going to see that the photons are going to be, of course, having a specific interaction with the electrons, and therefore we are going to have a conclusion that basically there's going to be a kind of a conservation of momentum. Now, the momentum from classical physics, we expect particles to be exhibiting this specific behavior, and therefore that's going to be backing up the wave particle duality nature of matter and waves. And this is going to be basically culminating into the various principles and, of course, data which is going to be backing up this aspect of quantum mechanics. Now, engage us in the various platforms that we're going to be, of course, involved in, and of course assist us in trying to reach out to more members through the various links which we're going to be providing on our YouTube channel and via social media pages. And I'd like to encourage our members also to subscribe, ring that notification bell, and also be following us in our various platforms which we are going to be involved. I'd like to wish us the best in our endeavors out there, of course, and wish us the best of luck. Let's meet in our next video. God bless you. Bye.